What if I told you that everything you learned today, every conversation, every insight, every piece of information you encountered, could vanish by tomorrow morning? Not because you have a medical condition, not because you're getting older, but because of something you might do tonight, or rather, something you might not do. Your brain is making a decision right now about what you'll remember and what you'll forget, and the single most important factor in that decision is whether you sleep tonight. This isn't motivational speaking. This is neuroscience. Right now, as you're watching this, temporary memory traces are forming in your brain. These traces are fragile. They're unstable. Without the right conditions, they'll fade within hours. But if you sleep tonight, really sleep, for the right amount of time, through the right sleep stages, your brain will perform a remarkable transformation. It will take those fragile traces and convert them into permanent memories. Memories you could recall decades from now. The difference between remembering and forgetting often comes down to a single night of sleep. Welcome to Serene Science Channel. I'm going to explain exactly how sleep and memory work together, what happens in your brain during sleep that makes memory permanent, and why sleep deprivation is one of the fastest ways to destroy your ability to learn and remember. If you want to understand how your brain actually works, not simplified pop science, but real neuroscience, explained clearly, subscribe to Serene Science Channel. We create long-form, evidence-based content about sleep, memory, and brain function. This video is part of our comprehensive series on sleep science. We've already covered how your brain falls asleep and what to do when your brain won't shut off at night. Now we're exploring the crucial relationship between sleep and memory. Hit subscribe, turn on notifications, and let's dive into the neuroscience of how sleep makes memory possible. Let's start with a fundamental question. Why do we remember anything at all? Your brain is constantly bombarded with information. Every second, millions of sensory inputs flood into your nervous system. Visual information, sounds, physical sensations, smells, internal states. It's overwhelming. If your brain tried to permanently store everything you experience, you'd run out of neural capacity almost immediately. More importantly, you'd be paralyzed by an inability to distinguish important information from trivial details. So your brain has evolved a sophisticated filtering and storage system. This system has three main stages: encoding, consolidation, and retrieval. Encoding is the initial formation of a memory trace. When you experience something, let us say you meet someone new and learn their name, neurons in your brain fire in a specific pattern. This pattern of neural activity is the physical basis of the memory. But this initial encoding creates only a temporary trace. The neural connections involved are weak and unstable. This is why you might remember someone's name immediately after hearing it, but forget it minutes later if you're distracted. For a memory to become permanent, it must go through consolidation. Consolidation is the process of stabilizing and strengthening the neural connections that encode a memory. It transforms a fragile, temporary trace into a robust, lasting one. And here's the crucial point. Consolidation happens primarily during sleep, not while you're awake. Not while you're resting quietly. During sleep, actual sleep with all its specific stages and neurodynamics, the third stage, retrieval, is your ability to access stored memories. You can't retrieve what hasn't been consolidated. This is why sleep is essential, not just for general brain health, but specifically for your ability to learn and remember. The relationship between sleep and memory is so fundamental that virtually every animal species that has been studied shows some form of sleep-dependent memory consolidation. From fruit flies to humans, sleep appears to be the brain's preferred state for making memories permanent. Let's explore how this works at the neural level. To understand how sleep affects memory, we need to look more closely at the 3 stages of memory formation: encoding, consolidation, and retrieval. Encoding begins when you pay attention to something. Attention is crucial. You cannot encode what you don't attend to. This is why you can drive a familiar route and have no memory of the journey. Your brain encoded nothing because your attention was elsewhere. When you do pay attention, specific neurons fire. The pattern of firing would neurons fire, in what sequence, with what timing constitutes the neural code for that particular experience or piece of information. This firing pattern creates temporary changes in the synapses. The connections between neurons, these changes are mediated by various molecular mechanisms. But the key point is that they're initially unstable. At the molecular level, encoding involves the activation of immediate early genes, the synthesis of new proteins, and temporary modifications to existing synaptic structures. All of this happens within seconds, 2 minutes of the initial experience. But these rapid changes are not sufficient for long-term storage. The synaptic modifications created during encoding are temporary. Without further processing, they'll reverse within hours. This is where consolidation becomes essential. Consolidation is the process of stabilizing memory traces. It involves structural and functional changes to neurons and synapses that make the memory resistant to forgetting. There are actually 2 types of consolidation: synaptic consolidation and systems consolidation. Synaptic consolidation occurs at the level of individual synapses. It involves the synthesis of new proteins, the growth of new dendritic spines, the tiny protrusions on neurons where most synapses form, and the strengthening of synaptic connections. This process takes hours and is relatively automatic. It doesn't require sleep, though sleep enhances it. Systems consolidation, on the other hand, is a slower process that reorganizes memories across different brain regions. This is where sleep becomes critical. During systems consolidation, memory is initially stored in the hippocampus, a structure deep in the temporal lobe that acts as a temporary memory buffer, are gradually transferred to the neocortex, the outer layer of the brain that serves as long-term storage. This transfer doesn't happen instantly. It's a gradual process that unfolds over days, weeks, or even months, and it happens primarily during sleep. Why does the brain use this 2-stage storage system? Why not just encode memories directly into long-term neocortical storage? The answer relates to the different computational strengths of the hippocampus and The hippocampus can rapidly encode new information without interfering with existing memories. It's specialized for fast learning. The neocortex, in contrast, learns slowly. It integrates new information gradually, weaving it into existing knowledge structures. This slow integration is necessary to prevent new learning from catastrophically overriding old memories. The hippocampus to neocortex transfer allows you to get the best of both systems. Rapid initial learning followed by gradual, integrative consolidation. And sleep is when this transfer primarily occurs. The 3rd stage of memory is retrieval, your ability to access stored information. Retrieval can be intentional, like when you try to remember someone's name, or automatic, like when a smell triggers a vivid memory. At the neural level, retrieval involves reactivating the pattern of neural activity that was present during encoding. If consolidation has strengthened the relevant synapses, this reactivation happens easily. If consolidation was inadequate, retrieval fails. This is why sleep is so important. Poor consolidation means poor retrieval. You might have the subjective sense that you learned something, but when you try to recall it later, the memory is simply not there. Sleep doesn't just affect how well you consolidate new memories. It also affects your ability to retrieve old ones. Sleep deprivation impairs retrieval even for well-consolidated memories. Studies show that people who are sleep deprived have difficulty accessing memories that they would normally retrieve easily when well rested. The memories are still there, but the retrieval process is impaired. Now that we understand the 3 stages of memory formation, let's look at what happens during sleep that makes consolidation possible. How sleep transforms temporary memories into permanent ones during sleep. Your brain is far from inactive. In fact, sleep is a time of intense neural activity, particularly in the circuits involved in memory. Let me describe what's happening in your brain during a typical night of sleep, focusing on memory consolidation. In the first third of the night, you spend most of your time in slow-wave sleep, also called deep sleep or N3 sleep. During slow-wave sleep, large populations of neurons in your cortex fire synchronously in a slow rhythm, about 1 cycle per second. They say arete, slow oscillations that give this sleep stage its name. These slow oscillations are not random. They coordinate the dialogue between the hippocampus and the neocortex. Here's the sequence. During the upstate of each slow oscillation, when cortical neurons are firing actively, the hippocampus replays memories from the previous day. The same neural patterns that fired during the day's experiences fire again, in compressed time. For example, if you spent an hour learning something new during the day, the neural pattern representing that experience might replay in seconds. During sleep, this replay is not a perfect reproduction, it's more like a highlight reel. The brain reactivates the most salient aspects of the experience. As the hippocampus replays these patterns, the neocortex listens. The cortical neurons that receive input from the hippocampus begin to strengthen their connections, gradually taking over representation of the memory. This process is coordinated by structures called sleep spindles and sharp wave ripples. Sleep spindles are brief bursts of brain activity, 12 to 15 cycles per second, that occur during both light and deep sleep. They appear to gate the flow of information from hippocampus to cortex, creating windows of opportunity for memory transfer. Sharp wave ripples are high-frequency bursts of activity in the hippocampus itself, occurring during the replay of memory patterns. Each ripple might represent the compressed replay of a behavioral sequence or learning episode. The coordination between slow oscillations, sleep spindles, and sharp wave ripples creates optimal conditions for systems consolidation. Studies show that artificially enhancing this coordination through techniques like acoustic stimulation timed to slow oscillations can improve memory consolidation. As the night progresses, your sleep architecture changes. You spend less time in deep slow-wave sleep and more time in REM sleep and lighter sleep stages. This shift is important for memory consolidation. Different types of memories appear to consolidate optimally during different sleep stages. During the middle hours of the night, you cycle through periods of light sleep, brief awakenings which you usually don't remember, and increasing amounts of REM sleep. Each cycle provides different computational opportunities for your brain. Light sleep may be important for integrating new information with existing knowledge networks. REM sleep, as we'll discuss later, plays a crucial role in consolidating procedural and emotional memories. In the last third of a normal night's sleep, REM sleep becomes dominant. You might spend 30 to 40 minutes in REM during a single cycle late in the night. During REM sleep, your brain is highly active, but in a different pattern than during slow-wave sleep. Instead of synchronized slow oscillations, you see rapid, desynchronized activity that resembles waking brain patterns. This is when your brain consolidates procedural memory skills, habits, and patterns. It's also when emotional memories are processed and integrated. We'll discuss REM sleep's specific contributions to memory in detail later. But the key point is this. A full night of sleep provides a sequence of different neural states, each contributing uniquely to memory consolidation. This is why even mild sleep restriction, cutting your sleep by an hour or two, can impair memory. You're not just losing sleep time. You're disrupting this precisely orchestrated sequence of consolidation processes. While the neural dynamics of sleep are crucial for memory consolidation, there's also important molecular and cellular work happening during sleep. During waking hours, your brain accumulates metabolic waste products, including proteins like beta-amyloid that are associated with Alzheimer's disease. Sleep activates the glymphatic system, a waste clearance pathway that removes these toxins. Sleep also regulates the synthesis of proteins necessary for synaptic plasticity. Many of the proteins required for strengthening synaptic connections are synthesized during sleep. Adityanaji sleep regulates genes involved in synaptic plasticity. Studies show that many immediate early genes that are activated during learning, show enhanced expression during subsequent sleep. All of this molecular machinery works in concert with the neural dynamics to transform temporary memory traces into permanent ones. Continuing with 18,000 plus more words on hippocampus, memory replay, sleep stages, sleep deprivation effects, practical applications, and future research. The hippocampus, your brain's memory consolidation center now. Let us explore the hippocampus in detail. The brain structure that is absolutely central to understanding sleep and memory. The hippocampus is a seahorse-shaped structure, hence its name. From the Greek hippos for horse and campos for sea monster, located deep in your temporal lobe. You actually have two hippocampi, one in each hemisphere. Despite its small size, each hippocampus is only about 4 centimeters long. This structure is arguably the most important brain region for memory formation. The hippocampus serves as your brain's rapid encoding system. When you experience something new, the hippocampus quickly creates a memory trace, a pattern of neural activity that represents that experience. This rapid encoding is possible because of the hippocampus's unique anatomy. It has a relatively simple, repetitive structure that allows it to quickly link together disparate pieces of information. For example, when you park your car in a specific location, your hippocampus binds together multiple elements. The visual appearance of the location, your spatial position, the time of day, perhaps how you were feeling. All of these separate pieces of information are linked into a unified memory trace. This binding function is critical for episodic memory, your memory for specific events and experiences. Without a functioning hippocampus, you cannot form new episodic memories. This was famously demonstrated in the case of patient HM, who had his hippocampi removed surgically to treat severe epilepsy. After the surgery, HM could no longer form new, long-term memories. He could hold information in working memory for a few minutes, but as soon as his attention was diverted, the information was lost forever. HM's tragic case revealed that the hippocampus is necessary for encoding new memories, but it also revealed something else. Old memories, formed before the surgery, were largely intact. This observation led to the two-stage model of memory storage that we discussed earlier. Memories are initially dependent on the hippocampus, but over time, through consolidation, they become independent of the hippocampus and are instead stored in the neocortex. The hippocampus has several distinct subregions, each with specific roles in memory processing. The dentate gyrus is the entry point for information into the hippocampus. It receives input from the entorhinal cortex, which itself receives information from virtually all cortical areas. The dentate gyrus performs a computation called pattern separation. It creates distinct neural representations for similar experiences. This is why you can remember going to the same restaurant on different occasions as separate events, rather than blending them all together. From the dentate gyrus, information flows to region C. A3K stands for cornu. Ammonis Latin. Foreign. Another name for the hippocampus, CA3, is a heavily interconnected region where neurons talk to each other extensively. This recurrent connectivity allows CA3 to perform pattern completion, retrieving a complete memory from a partial cue. This is why hearing a fragment of a song can bring back a vivid memory of where you first heard it. The partial cue, the song fragment, activates the complete memory trace through pattern completion in CA3. Finally, information flows to region CA1, which is the main output of the hippocampus, sending information back to the cortex. During sleep, this entire circuit becomes active in a specific way that facilitates memory consolidation. During slow-wave sleep, the hippocampus shows a characteristic pattern of activity called sharp wave ripples. These ripples are brief, 50 to 100 milliseconds, but intense bursts of synchronized neural firing. They occur primarily during the quiet periods of slow-wave sleep, when the cortex is in a down state of reduced activity. What's remarkable about sharp wave ripples is their content. During these events, the hippocampus is replaying memories from recent waking experience. Researchers have demonstrated this through recording studies in animals. They record from multiple hippocampal neurons while an animal learns a new task or explores a new environment. Then they record from the same neurons during subsequent sleep. What they find is striking. During sleep, the same sequences of neural firing that occurred during the waking experience fire again during sharp wave ripples. The brain is literally replaying the experience. But this replay is not just a passive recording. It is compressed in time. Sequences that took minutes or hours during waking replay in seconds during sleep. It's also selective. The brain doesn't replay everything equally, but prioritizes certain experiences based on factors like emotional significance and novelty. These sharp wave ripples drive the transfer of information from hippocampus to cortex. During each ripple, the hippocampus sends a compressed burst of information to the cortex. The cortex, if it's in the right state, which is coordinated by sleep spindles and slow oscillations, receives this information and gradually incorporates it into long-term storage. Over many nights of sleep, memories that initially depended entirely on the hippocampus gradually become independent of it, now represented in distributed cortical networks. This process explains why damage to the hippocampus typically affects recent memories more than remote ones. Recent memories haven't completed the consolidation process and still depend heavily on the hippocampus. Remote memories have been consolidated into the cortex and can survive hippocampal damage. Hippocampus, size and memory, performance. Individual differences in hippocampal size correlate with individual differences in memory performance. People with larger hippocampi tend to perform better on memory tasks, particularly spatial memory tasks. Interestingly, the hippocampus is one of the few brain regions that can generate new neurons in adulthood, a process called adult neurogenesis. These new neurons appear to play a role in memory formation, particularly in distinguishing similar experiences. Factors that enhance neurogenesis, like exercise learning and adequate sleep, also tend to enhance memory. Factors that impair neurogenesis, like chronic stress, aging, and sleep deprivation, impair memory. This brings us to a crucial point. Sleep deprivation doesn't just prevent the consolidation of existing memories. It may actually damage the hippocampus itself. Studies in animals show that chronic sleep deprivation reduces hippocampal neurogenesis, causes dendritic atrophy, shrinkage of neuronal branches, and impairs hippocampal plasticity. In humans, chronic sleep restriction is associated with reduced hippocampal volume. The hippocampus is particularly vulnerable to sleep loss, perhaps because it is so metabolically active and because it depends on precise timing and coordination of neural activity. Timing that's disrupted by inadequate sleep Memory replay during sleep, what your brain does at night. Let us dive deeper into one of the most fascinating discoveries in sleep and memory research. Memory replay. We've touched on this already, but it is worth exploring in detail because it is such a clear demonstration of active memory processing during sleep. Discovering memory replay. The discovery of memory replay happened gradually through clever experiments in animals, particularly rats. In a classic study from the 1990s, researchers implanted electrodes in the hippocampi of rats and recorded from many neurons simultaneously while the rats ran through a maze. Each location in the maze was associated with specific neurons firing. These are called place cells. As a rat ran through the maze, the researchers could track which neurons were firing and thus determine where the rat was, just by looking at the pattern of neural activity. Then, they let the rats sleep. And during sleep, they saw something remarkable. The same sequences of place cell firing that occurred when the rat was actually running through the maze occurred again during sleep. The brain was replaying the maze experience, not just random activation, but the actual sequences of neural activity that represented the rat's journey through the maze. And this replay was not identical to the original experience. It was compressed in time. A journey that took 30 seconds in real life might replay in just 1 to 2 seconds during sleep. This discovery raised obvious questions. Is the brain just randomly activating old memories? Or is this replay serving a function? Does it contribute to memory consolidation? Replay and memory consolidation. Subsequent research has shown that replay is not just epiphenomenal, a byproduct with no function. It's directly involved in memory consolidation. Here's the evidence. First, the amount of replay predicts memory performance. Animals and humans that show more replay of a learning experience during subsequent sleep show better memory for that experience when tested later. Second, disrupting replay disrupts memory consolidation. Researchers can selectively detect when replay is occurring based on specific patterns of neural activity and deliver an intervention, like a mild sensory stimulus, that interrupts the replay without disrupting sleep overall. When they do this, memory consolidation is impaired. Third, enhancing replay enhances consolidation. Researchers can use techniques like targeted memory reactivation, presenting cues during sleep associated with specific memories, to increase replay of those memories. This typically improves retention of the cued information. All of this evidence points to the same conclusion. Replay is not just a correlate of consolidation. It's a mechanism of consolidation. The brain is actively processing memories during sleep through this replay process. What determines what gets replayed? Your brain doesn't replay every experience equally. Some experiences are replayed more than others. What determines this selectivity? Several factors influence replay frequency. Novel experiences are replayed more than familiar ones. This makes sense. Novel information is more likely to need consolidation, while familiar information is already well encoded. Reward. Experiences associated with reward are replayed more. This is likely an adaptive mechanism. The brain prioritizes consolidating information about what led to positive outcomes. Emotional significance. Emotionally significant events, whether positive or negative, are replayed more than neutral events. Expectation violation. When reality violates your expectations, this mismatch is strongly replayed. Your brain seems to prioritize consolidating information that updates your model of how the world works. Intentional tagging. When you deliberately try to remember something, when you pay attention and rehearse it, you increase the likelihood it will be replayed during subsequent sleep. This selectivity is important. Your brain cannot consolidate everything you experience. It must prioritize. The factors that increase replay are the same factors that make information important or useful. Novelty, reward, emotion, surprise, and intentional encoding. This is why sleep is more important after days when you're relearning a lot of new information than after routine days. Your brain has more work to do, more new memories to consolidate. Replay beyond the hippocampus. While hippocampal replay has been most extensively studied, replay is not limited to the hippocampus. Replay has been observed in many cortical areas, particularly in regions involved in motor control and sensory processing. For example, when an animal learns a new motor skill, neurons in motor cortex that were active during skill performance reactivate during subsequent sleep in the same sequences. This cortical replay appears to contribute to motor memory consolidation. Similarly, after exposure to a novel sensory experience, sensory cortical areas show replay during sleep. This may help consolidate perceptual learning. The relationship between hippocampal and cortical replay is complex. In some cases, hippocampal replay appears to drive cortical replay, consistent with the idea that the hippocampus orchestrates systems consolidation. In other cases, particularly for motor and perceptual memories that may not involve the hippocampus as heavily, cortical replay can occur relatively independently, but the general principle is the same. During sleep, your brain reactivates the neural patterns that were active during waking experience, and this reactivation is a mechanism of memory consolidation. Forward and reverse replay. Interestingly, memory replay during sleep doesn't always occur in the same direction as the original experience. Sometimes replay occurs in the forward direction, the same sequence as during the experience, but sometimes it occurs in reverse, backwards from the endpoint to the beginning. Why would the brain replay experiences backwards? One hypothesis is that reverse replay serves a different computational function than forward replay. Forward replay might strengthen the memory trace as it was originally encoded. Reverse replay might help link outcomes, which occur at the end of a sequence, back to earlier actions and decisions. For example, if you're learning a maze and eventually find the reward, reverse replay during sleep might help you learn which earlier choices led to that successful outcome. Both forward and reverse replay appear to contribute to memory consolidation, possibly serving complementary functions in how memories are processed and integrated. Different sleep stages and different types of memory. We've talked about sleep as if it's a single state, but of course, it's not. Sleep consists of multiple distinct stages, each with different brain activity, patterns, and different functions for memory. Let's explore how different sleep stages contribute to consolidating different types of memories. Types of memory. A brief taxonomy. Before we can discuss how different sleep stages consolidate different memories, we need to clarify what types of memories exist. Memory researchers typically divide long-term memory into two main categories: declarative and non-declarative. Declarative memory is memory for facts and events, things you can consciously recall and declare. This includes episodic memory, memory for specific personal experiences, your memory of what you did yesterday, your first day of school, your last vacation. These are episodic memories. Semantic memory, memory for general knowledge and facts. Your knowledge that Paris is the capital of France, that water freezes at 0 degrees Celsius, that dogs are mammals. These are semantic memories. Declarative memories are what most people think of when they think of memory. They're conscious, explicit memories that you can verbally describe. Non-declarative memory, also called implicit memory or procedural memory, is memory that influences behavior without conscious awareness. These include this procedural memory, memory for skills and habits, your ability to ride a bike, type on a keyboard, play a musical instrument. These are procedural memories. Perceptual learning. improved ability to perceive stimuli. The gradual improvement in your ability to distinguish similar sounds when learning a new language is perceptual learning. Priming, changes in the ability to perceive or process a stimulus as a result of prior exposure. The fact that you recognize a word faster the second time you see it, even if you don't consciously remember seeing it before, is priming. Conditioning. Learned associations between stimuli and responses. Your learned fear response to a previously neutral stimulus that was paired with something negative is a form of conditioning. Non-declarative memories are typically unconscious. You may not even be aware that you have them, but they influence your behavior nonetheless. Different types of memories depend on different brain systems. Declarative memory depends heavily on the hippocampus and related structures in the medial temporal lobe. Non-declarative memory depends on various other systems. The basal ganglia for procedural memory, the amygdala for emotional conditioning, various cortical areas for perceptual learning, and critically for our purposes, different types of memories consolidate during different sleep stages. Slow-wave sleep and declarative memory. Slow-wave sleep, particularly the deepest stage N3, is crucial for consolidating declarative memories. The evidence for this comes from multiple lines of research, correlation, studies. The amount of slow-wave sleep someone gets after learning predicts how well they retain declarative information. More slow-wave sleep equals better memory. Manipulation studies. When researchers selectively reduce slow-wave sleep while keeping total sleep time constant, declarative memory consolidation is impaired. Conversely, when they enhance slow-wave sleep through techniques like acoustic stimulation, declarative memory improves. Brain imaging studies. When people are scanned while sleeping after learning declarative information, the same brain regions active during learning, particularly the hippocampus and medial prefrontal cortex, show reactivation during slow-wave sleep. This reactivation correlates with memory improvement. Why is slow-wave sleep so important for declarative memory? As we discussed earlier, slow-wave sleep is when the hippocampus replays memories and transfers them to the cortex. The slow oscillations, sleep spindles, and sharp wave ripples that characterize this stage create optimal conditions for hippocampal cortical dialogue. But there's more to it than just replay. Slow-wave sleep also affects the molecular and cellular mechanisms of consolidation. During slow-wave sleep, there's increased synthesis of proteins necessary for synaptic strengthening. There's also increased expression of genes involved in synaptic plasticity. All of this molecular machinery is necessary for making memory traces permanent. Additionally, slow-wave sleep is when the glymphatic system is most active, clearing metabolic waste products that could interfere with synaptic function. The combination of optimal neurodynamics, replay and transfer, molecular support, protein synthesis, and gene expression, and waste clearance makes slow-wave sleep uniquely suited for declarative memory, consolidation, REM sleep, and procedural memory. If slow-wave sleep is for declarative memory, REM sleep appears to be particularly important for procedural memory, skills, habits, and motor learning. The evidence here is equally strong. Correlation studies. After learning a new motor skill, people show increased REM sleep, particularly late in the night. The amount of this REM increase correlates with how much the skill improves overnight. Manipulation studies. Selectively depriving people of REM sleep while allowing slow-wave sleep impairs procedural memory consolidation. People don't show the typical overnight improvement in motor skills when REM'd. Brain imaging studies. Brain regions involved in motor learning, like motor cortex, cerebellum, and basal ganglia, show reactivation during REM sleep after motor skill learning. Why would REM sleep be specialized for procedural memory? One hypothesis relates to the unique neurochemical environment of REM sleep. During REM, the brain is flooded with this specific neurochemical milieu may be optimal for the type of plasticity required for skill learning. Another hypothesis relates to brain connectivity. During REM, there's extensive communication between motor areas, subcortical structures involved in habit learning, and cortical areas involved in motor planning. This network-wide coordination may facilitate motor memory consolidation. REM sleep also appears to be important for integrating new motor skills with existing motor repertoires. When you learn a new skill, you need to not only remember the specific movements, but also learn when and how to deploy this skill in context. REM sleep may help with this integration. REM sleep and emotional memory. In addition to procedural memory, REM sleep appears to play a unique role in processing emotional memories. This might seem unrelated to procedural memory, but from a neural perspective, there are connections. Both emotional processing and procedural learning involve subcortical structures and benefit from the specific neurochemical environment of REM. Studies show that emotional memories are preferentially consolidated during REM sleep. Emotionally arousing information is better remembered after sleep than neutral information, and this effect is particularly associated with REM sleep. Interestingly, REM sleep appears to consolidate the content of emotional memories while reducing their emotional charge. After REM-rich sleep, people can remember emotional events without experiencing the same intensity of emotion as when the event first occurred. This has led to theories that REM sleep serves an emotional regulation function, helping us process and integrate emotional experiences without being overwhelmed by them. Disruptions in REM sleep are associated with mood disorders and PTSD, conditions characterized by problems with emotional regulation and recurring intrusive memories. This suggests that healthy REM sleep is important not just for memory consolidation, but for emotional health more broadly. Light sleep, the underappreciated stage when people think about memory and sleep. They often focus on deep slow-wave sleep and REM sleep, but light sleep stages, N1 and N2, also contribute to memory consolidation. Light sleep, particularly N2, is characterized by sleep spindles, those brief bursts of 12 to 15 Hz brain activity we mentioned earlier. Sleep spindles have been directly linked to memory consolidation. The density of sleep spindles, how many occur per minute, correlates with IQ and with various measures of cognitive function. People with more spindles tend to learn better and remember better. Experimentally, when researchers used targeted memory reactivation, presenting cues during sleep associated with specific memories, spindles often occur immediately after the cue, and the occurrence of spindles predicts whether the cued memory will be enhanced. This suggests that spindles are active markers of memory processing, not just passive brain rhythms. What's special about spindles? They appear to gate the flow of information into the cortex. When a spindle occurs, cortical neurons are particularly responsive to inputs from the thalamus and hippocampus. This creates a brief window where new information can be incorporated into cortical networks. Light sleep is also when sleep spindles and slow oscillations begin to interact. Even though N2 is not characterized by the large, regular, slow oscillations seen in N3, there are still slow fluctuations in activity. When spindles occur during the upstate of these slow fluctuations, memory consolidation appears to be particularly effective. The whole night matters a crucial point. Optimal memory consolidation requires the full complement of sleep stages and their natural proportions and sequence. This is why recommendations for good sleep aren't just about duration, but about quality and continuity. You need to go through complete sleep cycles, spending adequate time in each stage. When sleep is fragmented, even if total sleep time is adequate, memory consolidation suffers. This is because fragmentation disrupts the natural cycling through stages and can reduce time in specific stages, particularly slow-wave and REM sleep. Similarly, substances that alter sleep architecture can impair memory even without reducing total sleep time. Alcohol, for example, can increase time and light sleep, but suppresses REM sleep and disrupts sleep architecture. This impairs memory consolidation despite potentially not reducing total sleep duration. The brain has evolved to consolidate different types of memories during different sleep stages, taking advantage of the unique neural and neurochemical properties of each stage. For optimal memory function, you need all of them: sleep deprivation and memory failure. Now let's turn to what happens when you don't sleep. The effects of sleep deprivation on memory. This is not just theoretically interesting. It's immediately practical. Most people experience sleep deprivation regularly, whether from work demands, social obligations, or sleep disorders. Understanding how this affects memory can motivate better sleep habits and inform decisions about when to prioritize sleep. Acute total sleep deprivation. The most extreme form of sleep deprivation is total sleep deprivation, staying awake for 24 hours or more. The effects on memory are dramatic and multifaceted. Encoding impairment. First, sleep deprivation impairs your ability to encode new memories in the first place. A study at UC Berkeley used fMRI to scan people's brains while they tried to memorize information, comparing well-rested participants to those who'd been awake for 24 hours. The results were striking. In well-rested people, the hippocampus showed strong activation during memory encoding. In sleep-deprived people, hippocampal activation was significantly reduced. Functionally, this translated to about a 40% reduction in the ability to form new memories. The sleep-deprived participants remembered only about 60% as much information as the well-rested participants. Why does sleep deprivation impair encoding? Several factors are involved. Reduced attention. Sleep deprivation impairs attention, and you cannot encode what you don't attend to. Sleep-deprived people are more distractible and have difficulty maintaining sustained attention on a task. Hippocampal dysfunction. Sleep deprivation appears to directly impair hippocampal function. The neurons don't fire as reliably. Synaptic plasticity is reduced, and the overall computational efficiency of the hippocampus decreases. Altered neurochemistry. Sleep deprivation changes the balance of neurotransmitters in ways that impair plasticity. For example, it increases adenosine, which generally suppresses neural activity. Consolidation impairment. Even if you somehow manage to encode memories while sleep deprived, those memories won't consolidate properly without subsequent sleep. Remember, consolidation happens primarily during sleep. If you learn something on Monday, stay up all Monday night, and then sleep normally Tuesday night. You'll still have impaired memory for what you learned on Monday. The critical consolidation window was Monday night, and you missed it. This is why all-nighters before exams are counterproductive. Even if you cram more information into your head during the extra waking hours, you'll retain less of it without sleep for consolidation. You'd be better off studying less and sleeping more. Studies have quantified this. People who sleep after learning retain about 20 to 40% more information than people who stay awake for an equivalent time period. This sleep benefit is robust across different types of material and different retention intervals. Cumulative effects. Perhaps most concerning, the effects of sleep deprivation on memory are cumulative. A single night of total sleep deprivation impairs memory, but you can recover with subsequent good sleep. However, chronic sleep restriction, even HUST, will know -2 hours, less than you need each night, gradually erodes memory function in a way that's harder to recover from. Research by David Dinges and colleagues showed that sleeping just 6 hours per night for 2 weeks produces cognitive impairments, equivalent to staying awake for 24 hours straight. But subjectively, people don't realize how impaired they are. They adapt to feeling tired and think they're functioning normally, even as objective performance plummets. This is particularly concerning for students and professionals who chronically restrict sleep. They reoperating with significantly impaired memory function, but may not realize it because they've adapted to their impaired baseline. Partial sleep deprivation. More common than total sleep deprivation is partial sleep deprivation. Getting some sleep, but not enough. What counts as enough varies by individual, but most adults need 7 to 9 hours. Many get significantly less. Even partial sleep deprivation impairs memory, though the effects are more subtle than total deprivation. One night of getting 5 to 6 hours instead of 7 to 9 hours reduces memory consolidation by approximately 15 to 20%. This might not seem like much, but it accumulates over time. More importantly, partial sleep deprivation disproportionately reduces certain sleep stages. When you cut sleep short, you lose most of the late-night REM sleep, because REM becomes more prevalent in the later sleep cycles. This selectively impairs the consolidation of procedural and emotional memories. Conversely, if you go to bed late, but wake up at your normal time, you lose early night deep sleep. This impairs declarative memory consolidation. Either way, insufficient sleep means insufficient memory consolidation. Light sleep, the underappreciated stage when people think about memory and sleep. They often focus on deep slow-wave sleep and REM sleep, but light sleep stages, N1 and N2, also contribute to memory consolidation. Light sleep, particularly N2, is characterized by sleep spindles, those brief bursts of 12 to 15 Hz brain activity we mentioned earlier. Sleep spindles have been directly linked to memory consolidation. The density of sleep spindles, how many occur per minute, correlates with IQ and with various measures of cognitive function. People with more spindles tend to learn better and remember better. Experimentally, when researchers used targeted memory reactivation, presenting cues during sleep associated with specific memories, spindles often occur immediately after the cue, and the occurrence of spindles predicts whether the cued memory will be enhanced. This suggests that spindles are active markers of memory processing, not just passive brain rhythms. What's special about spindles? They appear to gate the flow of information into the cortex. When a spindle occurs, cortical neurons are particularly responsive to inputs from the thalamus and hippocampus. This creates a brief window where new information can be incorporated into cortical networks. Light sleep is also when sleep spindles and slow oscillations begin to interact. Even though N2 is not characterized by the large, regular, slow oscillations seen in N3, there are still slow fluctuations in activity. When spindles occur during the upstate of these slow fluctuations, memory consolidation appears to be particularly effective. The whole night matters a crucial point. Optimal memory consolidation requires the full complement of sleep stages and their natural proportions and sequence. This is why recommendations for good sleep aren't just about duration, but about quality and continuity. You need to go through complete sleep cycles, spending adequate time in each stage. When sleep is fragmented, even if total sleep time is adequate, memory consolidation suffers. This is because fragmentation disrupts the natural cycling through stages and can reduce time in specific stages, particularly slow-wave and REM sleep. Similarly, substances that alter sleep architecture can impair memory even without reducing total sleep time. Alcohol, for example, can increase time in light sleep, but suppresses REM sleep and disrupts sleep architecture. This impairs memory consolidation despite potentially not reducing total sleep duration. The brain has evolved to consolidate different types of memories during different sleep stages, taking advantage of the unique neural and neurochemical properties of each stage. For optimal memory function, you need all of them: sleep deprivation and memory failure. Now let's turn to what happens when you don't sleep. The effects of sleep deprivation on memory. This is not just theoretically interesting. It's immediately practical. Most people experience sleep deprivation regularly, whether from work demands, social obligations, or sleep disorders. Understanding how this affects memory can motivate better sleep habits and inform decisions about when to prioritize sleep. Acute total sleep deprivation. The most extreme form of sleep deprivation is total sleep deprivation. Staying awake for 24 hours or more. The effects on memory are dramatic and multifaceted. Encoding impairment. First, sleep deprivation impairs your ability to encode new memories in the first place. A study at UC Berkeley used fMRI to scan people's brains while they tried to memorize information, comparing well-rested participants to those who'd been awake for 24 hours. The results were striking. In well-rested people, the hippocampus showed strong activation during memory encoding. In sleep-deprived people, hippocampal activation was significantly reduced. Functionally, this translated to about a 40% reduction in the ability to form new memories. The sleep-deprived participants remembered only about 60% as much information as the well-rested participants. Why does sleep deprivation impair encoding? Several factors are involved. Reduced attention. Sleep deprivation impairs attention, and you cannot encode what you don't attend to. Sleep-deprived people are more distractible and have difficulty maintaining sustained attention on a task. Hippocampal dysfunction. Sleep deprivation appears to directly impair hippocampal function. The neurons don't fire as reliably. Synaptic plasticity is reduced, and the overall computational efficiency of the hippocampus decreases. Altered neurochemistry. Sleep deprivation changes the balance of neurotransmitters in ways that impair plasticity. For example, it increases adenosine, which generally suppresses neural activity. Consolidation impairment. Even if you somehow manage to encode memories while sleep deprived, those memories won't consolidate properly without subsequent sleep. Remember, consolidation happens primarily during sleep. If you learn something on Monday, stay up all Monday night, and then sleep normally Tuesday night. You'll still have impaired memory for what you learned on Monday. The critical consolidation window was Monday night, and you missed it. This is why all-nighters before exams are counterproductive. Even if you cram more information into your head during the extra waking hours, you'll retain less of it without sleep for consolidation. You'd be better off studying less and sleeping more. Studies have quantified this. People who sleep after learning retain about 20 to 40% more information than people who stay awake for an equivalent time period. This sleep benefit is robust across different types of material and different retention intervals. Cumulative effects. Perhaps most concerning, the effects of sleep deprivation on memory are cumulative. A single night of total sleep deprivation impairs memory, but you can recover with subsequent good sleep. However, chronic sleep restriction, even host, will know -2 hours, less than you need each night, gradually erodes memory function in a way that's harder to recover from. Research by David Dinges and colleagues showed that sleeping just 6 hours per night for 2 weeks produces cognitive impairments, equivalent to staying awake for 24 hours straight. But subjectively, people don't realize how impaired they are. They adapt to feeling tired and think they're functioning normally, even as objective performance plummets. This is particularly concerning for students and professionals who chronically restrict sleep. They reoperating with significantly impaired memory function, but may not realize it because they've adapted to their impaired baseline. Partial sleep deprivation. More common than total sleep deprivation is partial sleep deprivation. Getting some sleep, but not enough. What counts as enough varies by individual, but most adults need 7 to 9 hours. Many get significantly less. Even partial sleep deprivation impairs memory, though the effects are more subtle than total deprivation. One night of getting 5 to 6 hours instead of 7 to 9 hours reduces memory consolidation by approximately 15 to 20%. This might not seem like much, but it accumulates over time. More importantly, partial sleep deprivation disproportionately reduces certain sleep stages. When you cut sleep short, you lose most of the late-night REM sleep, because REM becomes more prevalent in the later sleep cycles. This selectively impairs the consolidation of procedural and emotional memories. Conversely, if you go to bed late, but wake up at your normal time, you lose early night deep sleep. This impairs declarative memory consolidation. Either way, insufficient sleep means insufficient memory consolidation. Sleep fragmentation. Another common form of sleep disruption is fragmentation, waking up multiple times during the night. This can occur due to sleep disorders like sleep apnea, external disturbances like a crying baby or noisy neighbors, or physiological factors like needing to urinate. Sleep fragmentation impairs memory even if total sleep time is adequate. This is because consolidation depends not just on being asleep, but on the specific neurodynamics that occur during undisturbed sleep. When sleep is fragmented, the natural architecture of sleep stages is disrupted. You might not spend adequate time in slow-wave sleep or REM sleep, even if you're in bed for 8 hours. Studies in both animals and humans show that fragmenting sleep produces memory impairment similar to reducing total sleep time, even when total sleep time is held constant. This has implications for parents of young children, people with sleep disorders, and anyone whose sleep is regularly interrupted. The memory impairment they experience may be significant, even if they're in bed for an adequate duration. Selective sleep stage deprivation. Researchers can selectively deprive people of specific sleep stages while allowing others. This is done by monitoring brain activity and waking people whenever they enter a particular stage. These studies have confirmed the stage-specific functions we discussed earlier. Slow-wave sleep deprivation specifically impairs declarative memory consolidation. Procedural memory is less affected. REM sleep deprivation specifically impairs procedural memory consolidation and emotional processing. Declarative memory is less affected. Light sleep disruption impairs both declarative and procedural memory, probably because light sleep is when sleep spindles occur, and spindles contribute to both types of consolidation. These studies demonstrate that memory consolidation is not a generic sleep effect, but depends on specific physiological processes that occur during specific sleep stages. Mechanisms of impairment. How does sleep deprivation impair memory at the cellular and molecular level? Several mechanisms are involved. Synaptic scaling during waking synapses. Connections between neurons tend to strengthen due to ongoing activity and learning. This is necessary for encoding new information, but it comes at a cost. Energy consumption and cellular stress. One function of sleep is synaptic down, a selective weakening of synapses to restore energy balance and prevent synaptic saturation. This process is important for maintaining the dynamic range of synaptic weights, which allows for continued learning. Sleep deprivation prevents this. As a result, synapses become saturated, unable to strengthen further. This impairs the ability to encode new memories. Metabolic stress. Neurons are metabolically expensive cells. They consume large amounts of energy and generate waste products. Sleep is when many of these waste products are cleared through the glymphatic system. Sleep deprivation leads to accumulation of metabolic waste, including potentially toxic proteins like beta. This creates a hostile cellular environment that impairs synaptic plasticity and neuronal function. Neurochemical imbalance. Sleep deprivation disrupts the balance of neurotransmitters and neuromodulators necessary for memory. For example, sleep deprivation leads to high levels of adenosine, which suppresses neural activity. It disrupts the normal cycling of acetylcholine, which is necessary for plasticity. It can lead to elevated cortisol, which impairs hippocampal function. All of these neurochemical changes make memory formation and consolidation less efficient. Cellular stress responses. Sleep deprivation activates cellular stress responses in neurons. This diverts resources away from plasticity-related processes toward survival and stress management. In the hippocampus, sleep deprivation has been shown to reduce the birth of new neurons, cause dendritic atrophy, shrinkage of neuronal branches, and impair long-term potentiation. A cellular mechanism of memory formation. Chronic sleep deprivation can even cause neuronal death in some brain regions, though this typically requires very severe, prolonged sleep restriction. Individual differences. In vulnerability, not everyone is equally affected by sleep deprivation. There are significant individual differences in vulnerability to sleep loss. Some people show severe cognitive impairment after even mild sleep restriction. Others seem relatively resistant, maintaining performance despite reduced sleep. These differences appear to be partly genetic. Variants in genes related to sleep regulation, neurotransmitter systems, and cellular stress responses all contribute to individual differences in sleep need and vulnerability to sleep loss. Age also matters. Adolescents and young adults generally need more sleep than older adults, and they're more impaired by sleep restriction. This is particularly concerning given that this age group often has the most irregular sleep schedules. Older adults may need slightly less sleep and may be somewhat less impaired by acute sleep loss, but they're more vulnerable to the long-term consequences of chronic sleep restriction. Long-term consequences. While most discussion of sleep deprivation focuses on acute effects, chronic sleep restriction has long-term consequences for memory and brain health. Epidemiological studies show that people who chronically sleep less than 7 hours per night have increased risk of cognitive decline as they age. They also have increased risk of developing dementia, including Alzheimer's disease. While these are correlational findings, it's possible that people who sleep less have other risk factors for a cognitive decline. The magnitude of the association is concerning and has been replicated across multiple large studies. The mechanism may involve the accumulation of beta amyloid and tau, proteins associated with Alzheimer's disease. Sleep is when these proteins are cleared from the brain. Chronic sleep restriction may allow them to accumulate too toxic levels over years or decades. This suggests that prioritizing good sleep throughout life may be important not just for current memory function, but for long-term brain health and reducing dementia risk. Continuing in next part due to length, practical implications, optimizing sleep for memory. Understanding the neuroscience of sleep and memory is intellectually interesting, but it's also practically important. Let's discuss how to apply this knowledge to optimize your own memory and learning. For students, strategic sleep scheduling. If you're a student, sleep should be a central part of your study strategy, not an afterthought. Here's what the research tells us. Study before sleep, not before exams. The optimal time to study material is before sleep, not immediately before a test. This gives your brain time to consolidate the information overnight. Many students do the opposite. They stay up late, studying the night before an exam. This is about the worst possible strategy. You're sleep depriving yourself, which impairs encoding and retrieval at the exact moment you need optimal memory function. A better strategy: study in the evening, sleep well, wake up refreshed, and take the exam. You'll retain more information and perform better on the test. Space study sessions with sleep. If you're learning complex material over multiple days or weeks, sleep between study sessions is crucial. Each night of sleep consolidates what you learned that day and prepares your brain for new learning the next day. Without adequate sleep, new learning interferes with previously learned material, and previously learned material interferes with new learning. This is called interference, and sleep helps prevent it. Naps for memory. Strategic napping can enhance learning, especially for declarative memory. A 60 to 90 minute nap after a study session can improve retention of the material. This is long enough to include some slow-wave sleep, which, as we've discussed, is when declarative memory consolidates. Shorter naps, 20 to 30 minutes, can improve alertness and attention, which indirectly benefits learning, but they're not long enough for significant memory consolidation. Avoid all-nighters. We've already discussed why all-nighters are counterproductive, but it's worth emphasizing. Research clearly shows that pulling an all-nighter before an exam reduces performance. The sleep deprivation impairs your ability to retrieve information you already know and to think clearly during the exam. If you must choose between 1 more hour of study and 1 more hour of sleep, choose sleep. The benefit to your memory and cognitive function will be greater than any marginal benefit from additional study time. Timing of different subjects. Given that different types of memory consolidate during different sleep stages, should you study different subjects at different times of day? This is speculative, but some research suggests that motor skills and procedural learning, like learning a musical instrument or a sport, might benefit from evening practice followed by sleep-rich and REM, which occurs more in late night and early morning. Factual studying, on the other hand, might benefit most from evening study followed by early night slow-wave sleep. However, these are subtle effects, and the most important factor is simply getting adequate total sleep of good quality. Don't overthink the timing. Just prioritize sleeping well consistently. For professionals, sleep is performance enhancement. If you're a professional, sleep is not a luxury or a sign of weak work ethic. It's a fundamental requirement for optimal cognitive performance. Meeting and presentation, scheduling, important meetings, presentations, or decision-making sessions should be scheduled when you're well rested, not after poor sleep. If you have a critical meeting on Tuesday, the sleep you get Monday night matters. Prioritizi Italiano. Decline social engagements. Finish work earlier. Do whatever is necessary to get adequate sleep before important cognitive demands. Learning new skills. If you're learning new professional skills, new software, new techniques, new procedures, ensure you're getting good sleep during the learning period. This is when your brain is consolidating procedural and declarative knowledge. Shortchanging sleep during training periods reduces the return on investment of the training time. Creative problem solving. The consolidation that occurs during sleep isn't just passive storage, it's active reorganization and integration. This is why sleeping on a problem often leads to insights. During sleep, your brain can explore connections between ideas that weren't obvious during waking hours. If you're stuck on a problem, work on it, then sleep. Don't stay up late trying to force a solution. Sleep is when creative insights often emerge. Chronic stress and sleep. High-stress professions often involve poor sleep, creating a vicious cycle. Stress impairs sleep. Poor sleep impairs cognitive function and stress resilience, which creates more stress. Breaking this cycle requires prioritizing sleep especially during stressful periods. This might mean setting boundaries around work hours, using stress reduction techniques before bed, or seeking professional help for stress management or sleep problems. For older adults, protecting memory through sleep. As we age, both sleep and memory change. Understanding these changes and their interaction is important for maintaining cognitive function. Age-related sleep changes. Older adults typically experience reduced total sleep time, reduced slow-wave sleep, more fragmented sleep with more awakenings. Earlier sleep timing, going to bed earlier and waking earlier. These changes are partly biological. The brain's sleep-generating mechanisms change with age, but they're also partly behavioral and environmental. Maintaining slow-wave sleep. Given that slow-wave sleep is so important for declarative memory, and given that it declines with age, maintaining slow-wave sleep might help protect memory in aging. How can you do this? Regular exercise, physical activity increases slow-wave sleep, particularly in older adults. Consistent sleep schedule. Irregular sleep schedules fragment sleep and reduce slow-wave sleep. Cool sleep environment. Slightly cool temperatures promote slow-wave sleep. Avoid alcohol. While it might help you fall asleep, alcohol suppresses slow-wave sleep, treating sleep disorders. Sleep disorders become more common with age. Sleep apnea, restless leg syndrome, insomnia, all can severely fragment sleep and impair memory. If you're experiencing poor sleep, seek evaluation and treatment. Treating sleep disorders can improve not just sleep, but also memory and overall cognitive function. Some studies suggest that treating sleep apnea in older adults can slow cognitive decline, though more research is needed. Sleep and dementia risk. As mentioned earlier, chronic poor sleep is associated with increased dementia risk. While we can't yet say definitively that improving sleep reduces dementia risk, that would require very long-term intervention studies. The association is strong enough that prioritizing good sleep seems prudent for brain health. This is particularly true given that poor sleep may contribute to amyloid accumulation. And amyloid accumulation is thought to begin decades before dementia symptoms appear. Good sleep throughout middle age and into older adulthood might be important for reducing long-term dementia risk. For everyone, practical sleep hygiene. Regardless of your age or occupation, certain sleep practices support memory, consolidation, consistency. Keep a regular sleep schedule. Go to bed and wake up at approximately the same time every day, including weekends. Why? Your circadian rhythm, internal biological clock, regulates sleep timing. When your sleep schedule is irregular, your circadian rhythm becomes misaligned, which can impair sleep quality and consolidation. Duration. Aim for 7 to 9 hours of sleep per night. Individual needs vary, but most adults fall in this range. How do you know if you're getting enough? If you feel alert and perform well during the day without caffeine, you're probably getting enough. If you need an alarm clock to wake up and feel groggy during the day, you probably need more sleep. Quality. Sleep quality matters as much as quantity. Fragmented or disturbed sleep impairs consolidation even if total sleep time is adequate. To improve sleep quality, make your bedroom dark, quiet, and cool. Use your bed only for sleep and sex, not for work or watching TV. Avoid screens, phone, computer, TV for an hour before bed. The blue light can suppress melatonin. Avoid caffeine after early afternoon. It stays in your system for 6+ hours. Avoid alcohol close to bedtime. It fragments sleep and suppresses REM. Exercise regularly, but not right before bed. Strategic napping. If you didn't sleep well the previous night, a nap can help, but timing matters. Naps earlier in the day, before 3 p.m., are less likely to interfere with nighttime sleep. Naps longer, 10-90 minutes, might leave you groggy. Sleep inertia when you wake up. A 60 to 90-minute nap can include slow-wave sleep and improved declarative memory consolidation. A 20 to 30-minute nap can improve alertness without significant sleep inertia. Targeted memory reactivation. This is an experimental technique, but it's worth mentioning as it might become practical in the future. The idea is to present cues during sleep, like specific sounds or smells, that were associated with information learned during the day. This can enhance consolidation of the cued information. Currently, this requires sleep monitoring equipment and is mostly used in research settings. But as sleep tracking technology improves, it might become feasible for personal use. What about sleep supplements and medications? Many people use supplements or medications to help with sleep. How do these affect memory consolidation? Melatonin. Melatonin is a hormone that regulates sleep timing. Supplemental melatonin can help with jet lag or shift work by helping shift your circadian rhythm. For memory consolidation, melatonin's effects are indirect. If it helps you sleep better or more consistently, it benefits memory. But melatonin doesn't directly enhance consolidation beyond its effects on sleep timing and quality. Typical doses are 0.3 to 3 milligrams. Higher doses aren't necessarily more effective. Over-the-counter sleep aids. Most OTC sleep aids, like diphenhydramine or doxylamine, are antihistamines that cause drowsiness. As a side effect, they can help you fall asleep, but they don't produce natural sleep architecture. They may suppress REM sleep and can leave you groggy the next day. For occasional use, they're probably fine, but they're not ideal for regular use, especially if memory consolidation is a priority. Prescription sleep medications. Medications like benzodiazepines or zolpidem, isoprene, can help with sleep onset and reduce awakenings. However, they alter sleep architecture. They generally reduce slow-wave sleep and may affect REM sleep. This could potentially impair memory consolidation. That said, for people with severe insomnia, the benefit of getting sleep with medication might outweigh the concerns about altered sleep architecture. This is something to discuss with a doctor, weighing the specific situation. Cannabis and CBD. Cannabis, particularly THC, can help some people fall asleep faster, but it suppresses REM sleep significantly. Regular use can lead to tolerance and withdrawal-related sleep problems. CBD, without THC, may help with anxiety-related sleep problems for some people, but evidence is still limited. Effects on sleep architecture and memory consolidation are not well. The bottom line on sleep aids: the goal should be natural, unmedicated sleep with normal architecture if possible. Sleep aids might be necessary in some situations, but they should be used thoughtfully, ideally with medical guidance, and with awareness that they may not produce optimal sleep for memory consolidation. Special populations and circumstances. Some groups face unique challenges for sleep and memory. Shift workers. Working night shifts or rotating shifts severely disrupts circadian rhythms and sleep quality. The memory impairment in chronic shift workers is well documented. Strategies to mitigate this include using bright light exposure during the night shift to shift circadian timing, sleeping in a completely dark room during the day, maintaining as consistent a schedule as possible, even on days off, strategic napping before or during shifts. Parents of young children. Sleep fragmentation from caring for infants and young children can significantly impair memory. This is unavoidable to some extent, but strategies to cope include napping when the baby naps, having partners alternate night duties when possible, accepting temporary cognitive impairment rather than adding stress by expecting normal performance, prioritizing sleep when possible, even if it means other tasks don't get done. People with chronic pain can fragment sleep and reduce slow-wave sleep, impairing memory. Optimal pain management. Working with healthcare providers can improve sleep and thereby improve memory. Sometimes treating sleep, for example, with cognitive behavioral therapy for insomnia, can also help reduce pain perception. Elite athletes. For athletes, sleep is crucial for motor memory, consolidation, and physical recovery. Many professional sports teams now employ sleep coaches and prioritize sleep as part of training regimens. Practices include consistent sleep schedules, even during travel, strategic napping around training sessions, sleep environment optimization. Education about sleep's role in skill learning and performance, the future of sleep and memory research. While we've learned enormous amounts about sleep and memory over the last few decades, there's still much we don't understand. Let's explore the frontiers of this research and where the field is heading. Precision sleep interventions. One exciting direction is the development of targeted interventions to enhance specific aspects of sleep for memory consolidation. Closed-loop acoustic stimulation. Researchers have developed systems that monitor brain activity in real time and deliver precise acoustic stimuli during specific sleep phases. For example, the system might detect slow oscillations during slow-wave sleep and deliver gentle sounds, like soft tones, timed to the peaks of these oscillations. This can enhance the amplitude of slow oscillations and improve memory consolidation. In experimental settings, this technique has improved memory by 10 to 20% compared to sham stimulation. It's particularly effective for declarative memory. The potential applications are significant. Imagine a device you wear to bed that automatically optimizes your sleep for memory consolidation. This could be especially valuable for students, professionals learning new skills, or older adults trying to maintain cognitive function. Current systems require expensive EEG equipment, but as technology improves, consumer versions might become available. Pharmacological enhancement. While we discussed sleep medications earlier in the context of their potential downsides, there's active research into medications that might enhance sleep-dependent memory consolidation without disturbing natural sleep architecture. Some candidates include medications that enhance slow oscillations specifically, compounds that modulate specific neurotransmitter systems during sleep to enhance plasticity, drugs that increase neurogenesis or synaptic growth specifically during sleep. This is still largely experimental, but the goal is to develop interventions that give you the memory benefits of good sleep, even if life circumstances prevent optimal natural sleep. Transcranial stimulation. Non-invasive brain stimulation techniques like transcranial direct current stimulation, TDCS, or transcranial magnetic stimulation, TMS, can modulate brain activity. Some research has shown that applying these techniques during sleep can enhance slow oscillations and improve memory consolidation. This approach is still experimental and not ready for consumer use, but it represents another potential avenue for sleep enhancement. Understanding individual differences, we know there are substantial individual differences in sleep need, sleep architecture, and responses to sleep deprivation. Understanding the basis of these differences is an active research area. Genetic factors. Twin and family studies show that sleep characteristics are highly heritable. Researchers are identifying specific genes that influence sleep duration, how much you need, sleep timing, whether you're a morning person or a night person, sleep depth, or much slow-wave sleep, you naturally get vulnerability to sleep deprivation. One famous example is the DEC2 mutation, which allows some people to function well on just 4 to 6 hours of sleep per night. These individuals appear to get more efficient sleep, more slow-wave sleep in less total time. Understanding these genetic factors could eventually lead to personalized sleep recommendations based on genetic testing. Age-related changes. We know sleep changes with age, but we don't fully understand why or whether these changes are necessary or modifiable. Some research suggests that age-related decline in sleep quality, particularly reduced slow-wave sleep, contributes to age-related memory decline. If so, interventions to maintain slow-wave sleep might help maintain memory and aging. Other research is exploring whether age-related changes in circadian rhythms, like earlier wake times, are adaptive or whether they should be counteracted. Sex differences. There are interesting sex differences in sleep that aren't fully understood. Women tend to have more slow-wave sleep than men, and may be more vulnerable to certain types of sleep disruption. Men are more likely to have sleep apnea. These differences may relate to hormonal factors, but the mechanisms aren't clear. Understanding sex differences could lead to sex-specific recommendations for optimizing sleep for memory. Sleep and creativity. An emerging research area is the relationship between sleep and creativity. It's long been observed anecdotally that creative insights often occur after sleep. The chemist, August Kakul, supposedly discovered the ring structure of benzene after dreaming of a snake eating its own tail. Paul McCartney claimed the melody for Yesterday came to him in a dream. Recent research is trying to understand the mechanisms, REM sleep, and REM sleep appears to enhance creative problem solving, particularly for problems that require making non-obvious connections between ideas. In one study, people worked on creative problems, then either stayed awake, napped without REM, or napped with REM. The REM group showed the greatest improvement in creative problem solving. The hypothesis is that REM sleep's unique neural dynamics, particularly the activation of association cortices, in the absence of executive control, allow the brain to explore unusual combinations of ideas, sleep and insight. Sleep doesn't just consolidate existing knowledge, it can transform it, leading to insights that weren't available during waking hours. One classic demonstration. People learned a complex math task that had a hidden shortcut. Only about 20% discover the shortcut if they stayed awake, but about 60% discovered it after sleep. Sleep appears to extract hidden rules and patterns from learned information, facilitating insights. This has implications beyond memory, per se. If sleep enhances creativity and insight, this is another reason to prioritize adequate sleep, especially during creative work or problem. Sleep and forgetting. Interestingly, sleep doesn't just help you remember, it also helps you forget. This might sound contradictory, but it's actually important. Your brain can't store everything. It needs to be selective about what to consolidate and what to let fade. Sleep appears to facilitate both processes, strengthening important memories while allowing unimportant ones to weaken. Some research suggests that sleep helps you forget the specific details of experiences while retaining their gist or meaning. This could be adaptive. You don't need to remember every detail of every meal you've eaten, but you might need to remember general patterns, like which restaurants you enjoy. There's also fascinating research on motivated forgetting during sleep, using cues during sleep to help people unlearn unwanted associations, like fears or bad habits. This is very preliminary, but could have applications for treating anxiety disorders or addiction. Memory, integration, and abstraction. Beyond simply strengthening individual memories, sleep appears to integrate new information with existing knowledge and extract abstract rules or patterns. For example, if you learn multiple related facts during the day, sleep doesn't just consolidate each fact independently. It helps you extract the relationships between the facts and integrate them into a coherent knowledge structure. This is sometimes called schema consolidation. Sleep helps you build and refine mental schemas or frameworks for organizing knowledge. Similarly, if you're learning a skill through multiple examples, sleep helps you abstract the general principle underlying the examples. You don't just remember the specific instances, you extract the rule. This integration and abstraction function of sleep may be as important as simple consolidation. It's what allows new learning to become meaningful and applicable, rather than just a collection of isolated facts. Research is ongoing to understand the neural mechanisms of this process and how it can be enhanced. Sleep and memory across the lifespan. Most sleep and memory research has focused on adults, but understanding how this relationship changes across the lifespan is important. Infancy and childhood. Infants sleep a lot, 16+ hours per day, and sleep architecture changes dramatically in early life. This early sleep is thought to be crucial for brain development and for learning the immense amount of information infants and young children need to acquire. However, studying memory consolidation in preverbal children is methodologically challenging. Some research suggests that even brief naps enhance memory consolidation in young children, and that children who nap learn better than those who don't. This has implications for preschool and kindergarten nap policies. Adolescents have a biological shift toward later sleep timing. Going to bed later and waking later is conflicts with early school start times, leading to chronic sleep restriction. Given that adolescence is a critical period for learning and that the adolescent brain is still developing, the widespread sleep deprivation in this age group is concerning. Research is documenting the effects of early school start times on memory and academic performance, with some studies showing significant improvements when schools shift to later start times. Aging, as we've discussed, sleep deteriorates with age, which may contribute to age-related memory decline, but there's still much to understand. Are age-related sleep changes inevitable and potentially even adaptive? Or should we be more aggressively treating sleep problems in older adults to preserve memory? Some exciting preliminary research suggests that interventions to improve sleep in older adults through cognitive behavioral therapy, exercise, or even brain stimulation can improve memory performance. This suggests that at least some age-related memory decline might be preventable through sleep optimization. Technological advances. Technology is creating new opportunities for sleep and memory research. Portable EEG. Consumer sleep tracking devices are becoming increasingly sophisticated. While most don't yet provide research-grade data, they're improving. This could enable large-scale studies of sleep and memory in naturalistic settings, rather than just in sleep labs. It could also enable personalized feedback about how your specific sleep patterns affect your memory. Artificial intelligence, machine learning algorithms are being applied to sleep data to predict which sleep patterns will lead to optimal memory consolidation for specific individuals. The brain's response to sleep is complex and individual. AI might be able to find patterns in this complexity that allow for truly personalized sleep optimization. Brain-computer interfaces. As brain-computer interface technology advances, it might become possible to more precisely modulate sleep in real time to enhance specific cognitive functions, including memory. This is still far in the future, but the basic research is being done now. Virtual reality. VR is being used to create controlled learning experiences followed by sleep, allowing researchers to study memory consolidation for complex, immersive experiences. This could help us understand how sleep consolidates real-world learning, which is often complex and multimodal rather than just simple lab tasks. Unanswered questions. Despite all we've learned, major questions remain. Why did sleep evolve for memory consolidation? Why couldn't evolution find a way to consolidate memories during waking hours? What is it about the sleep state that makes consolidation more efficient or effective? Some theories suggest that sleep provides a dedicated time for memory processing without interference from ongoing sensory input and encoding. Others suggest that sleep's unique neurochemical environment is necessary for certain types of plasticity. How much sleep do different people really need? We have general guidelines, but individual variation is substantial. How can we determine optimal sleep duration for a specific person? Can we compensate for lost sleep? If you miss sleep one night, can you fully recover by sleeping more on subsequent nights, or is there permanent impairment? Short-term recovery is possible, but for chronic sleep restriction, the answer is less clear. What's the evolutionary function of REM sleep? REM is metabolically expensive and potentially dangerous. You're paralyzed and less responsive to threats. Why did it evolve? Is its role in memory consolidation sufficient to explain its evolutionary persistence? How do dreams relate to memory consolidation? We experience vivid dreams, especially during REM sleep. Are dreams a byproduct of memory, consolidation, or do they serve a function? This remains controversial. Some researchers think dreams are meaningless noise, the subjective experience of random neural activation during sleep. Others think dreams serve specific functions, like emotional processing or memory integration. Clinical applications. Understanding sleep and memory has clinical implications for various conditions. Alzheimer's disease. Alzheimer's is characterized by progressive memory loss. There's increasing evidence that sleep disruption contributes to Alzheimer's pathology. Sleep is when the brain clears amyloid beta, a protein that accumulates in Alzheimer's. Poor sleep may lead to amyloid accumulation over years or decades. Some researchers are investigating whether improving sleep through behavioral interventions or medications could slow Alzheimer's progression or even reduce risk of developing the disease. PTSD, post-traumatic stress disorder, involves both intrusive memories and disrupted sleep, particularly REM sleep. Some researchers think that disrupted REM sleep prevents normal emotional processing of traumatic memories, leading to the symptoms of PTSD. Treatments that improve sleep, particularly REM sleep, might help with PTSD symptoms. Some preliminary research supports this idea. Depression. Depression is associated with both memory problems and sleep disruption. The relationship is bidirectional. Depression causes sleep problems, and sleep problems worsen depression. Treating sleep, often with cognitive behavioral therapy for insomnia, can improve both sleep and depression symptoms. Schizophrenia. People with schizophrenia often have severe sleep disruption and memory impairments. Some research suggests that sleep problems might contribute to cognitive symptoms of schizophrenia. Improving sleep might help with these cognitive symptoms. Learning disorders. Some learning disorders may involve problems with memory consolidation. If sleep-dependent consolidation is impaired in learning disorders, sleep interventions might help. This is an active research area. Summary and key takeaways. We've covered an enormous amount of ground. Let me summarize the key points about sleep and memory. The fundamental relationships sleep and memory are inseparable. Memory consolidation, the process of making memories permanent, happens primarily during sleep, not during waking hours. Without adequate sleep, memories remain fragile and vulnerable to forgetting. With good sleep, memories become stable and integrated into your long-term knowledge. This relationship is not optional or luxury. It's a biological necessity. Your brain evolved to consolidate memories during sleep, and there's no known way to circumvent this requirement. The stages of memory formation. Memory formation involves 3 stages. 1. Encoding, creating the initial memory trace during waking experience. 2. Consolidation, stabilizing and strengthening the memory, primarily during sleep. 3. Retrieval, accessing the stored memory. Sleep is most critical for consolidation, but also affects encoding. You encode poorly when sleep deprived, and retrieval, you retrieve poorly when sleep deprived. The role of the hippocampus is your brain's rapid encoding system and temporary memory buffer. During sleep, the hippocampus replays memories and transfers them to the cortex for long-term storage. This hippocampal cortical dialogue, coordinated by slow oscillations, sleep spindles, and shockwave ripples, is the neural mechanism of systems consolidation. Different sleep stages for different memories. Different types of memories consolidate during different sleep stages. Slow wave sleep consolidates declarative memories, facts, and events. REM sleep consolidates procedural memories, skills, and habits, and processes emotional memories. Light sleep contributes to both types of consolidation, particularly through sleep spindles. A full night of sleep, cycling through all stages, is necessary for optimal consolidation of all types of memories. The devastating effects of sleep deprivation. Sleep deprivation impairs memory through multiple mechanisms. Encoding failure. Sleep-deprived brains struggle to form new memories. Consolidation failure. Memories can't consolidate without adequate sleep retrieval impairment. Even well-consolidated memories are harder to access when sleep-deprived. These effects occur with both total sleep deprivation and partial sleep restriction, even losing 1 to 2 hours of sleep per night significantly impairs memory over time. Practical applications: you can apply this knowledge. Students, study before sleep. Avoid all-nighters. Use strategic napping. Professionals, schedule important cognitive work when well-rested. Sleep on problems. Protect sleep during learning periods. Older adults, maintain sleep quality to protect memory. Treat sleep disorders. Everyone, practice good sleep hygiene. Consistent schedule. Adequate duration. Optimal environment. The future research continues on. Targeted sleep interventions to enhance consolidation. Understanding individual differences in sleep, need and response, sleep's role in creativity and insight. Clinical applications for memory disorders. Technology for personalized sleep optimization. The bottom line: if you remember only one thing from this video, remember this. Sleep is not time away from living and learning. Sleep is when your brain processes and consolidates your waking experiences, transforming them into lasting knowledge and skills. Shortchanging your sleep shortchanges your memory and your ability to learn. Prioritizing sleep is prioritizing your cognitive function and long-term brain health. We've explored the fascinating neuroscience of how sleep makes memory possible. From the molecular mechanisms in individual synapses to the large-scale neurodynamics of memory replay, from the different contributions of sleep stages to the devastating effects of sleep deprivation, we've seen that sleep is absolutely fundamental to memory and learning. This isn't abstract science, it's immediately relevant to your life. Every night, your brain makes decisions about what you'll remember and what you'll forget. Those decisions are profoundly influenced by the quality and quantity of your sleep. If you're a student, sleep is study time. If you're a professional, sleep is when you consolidate the day's learning and prepare for tomorrow's challenges. If you're aging, sleep might be one of the most important factors in maintaining your memory and reducing dementia risk. The evidence is clear. Prioritize your sleep. Protect it. Value it. It's not wasted time. It's when your brain is doing some of its most important work. Thank you for watching this episode of Serene Science Channel. If you found this information valuable, please subscribe for more evidence-based content on sleep, memory, and brain function. And tonight, when you lie down to sleep, you can appreciate that you're not just resting. You're allowing your brain to consolidate everything you learned today, building the memories that will shape who you are tomorrow. Sleep well, learn well, remember well.